Okay, now so Geodict has finished, and again the result viewer pops up. Here you get a report. And first of all, you have the engineering parameters, and there is the isotropic approximation. And as expected, when you make a unidirectional composite, the error of the isotropic approximation is really, really high. So that's not the values you should use. You can then go down, then you see something like engineering parameters in the original coordinate system. That means that are the parameters in the geodic coordinate system x, y, and z direction. You get a cubic approximation, you get an orthotropic approximation, and you see that the orthotropic error is quite low, so you can use the orthotropic approximation that is also expected in a unidirectional composite. And you can see that in E1 direction we have a really high stiffness, and in the two other directions the stiffness is quite low, also to be expected. Then you get results in the principal material axis. The principal material axis is important if your material has a main direction in itself, so maybe if all fibers were oriented under a certain angle or something like that. So Geodict tells you the principal material axis and also gives you the results in this coordinate system. There you can also get transverse isotropic approximation, and again the orthotropic approximation. Here you just have to be a little bit careful, because in Geodict, per definition, the stiffest direction is always 3 direction. But it's the same values. That's also to be expected, because in our material the main direction is aligned to one of the global directions, namely x direction. When you scroll down, then you also get the anisotropic stiffness tensor. You could use that to go on in another simulation software for macroscopic simulation or so on. If you click on plots, you get a stiffness plot, and stiffness is in different planes. Here you can also see the high degree of anisotropy, because the stiffnesses are highest in 0 and 180 degrees. So now we go to strain stress visualization, and here we can load the stress fields that Geodict say. For example, we can load the stresses in x direction. So click on load. You can choose which volume fields you want to load. In this case it's only 2, so you can click on OK. And then Geodict loads them into the user interface. And then you see that all the fibers are red. And the reason for that is that the default color for material ID 1 in Geodict is red. But if you have the color maps for the results, the red color is always a little bit misleading. So now we change the color of the fibers. We do that by going to this button and change it from red to light gray. And what you see now is the strain distribution in the polymer, and here you can see the fibers. Why do you see only the fibers as a structure and not also the polymer? The reason for that is again hidden behind this button. You can see here that material ID 1 is not visible, material ID 2 is visible. So we could also activate the polymer, and then we do not see any volume field anymore. But of course we want to look at the volume field, so it's a good idea to just hide the entire structure, and you can do that by this checkbox. And now you see the results. So now we go back to the result viewer, and in the next step I want to rerun the simulation, but then use downsampling. For those of you who saw my talk earlier on, you saw that downsampling can decrease the runtime significantly, and we will do that now. So to redo the simulation, we click on load structure. And you also can click on load input map. That loads all the simulation configurations you made before into the user interface again. That's especially important if you reopen a result after a day or a month or a year and you want to rerun the simulation. Okay, and I want to set all the parameters, of course, including the materials. Okay, so we minimize the result viewer, and there's the structure. And then we go back to ElastoDict. make sure that Freemoth Vox is chosen and click on Edit. You can see that the materials are still chosen. The load case is still defined. And the only change we have to make is here at the solver settings. And here we activate use downsampling. That means that 4x4x4 voxels are combined into one voxel, and also that the material laws of those voxels are mixed into one material law for this larger voxel. And this mixture is described by either laminate theory or arithmetic mean. And the laminate theory is the more accurate one in most cases, especially in a case like a composite, where you have only solid materials. So we stay with the laminate theory. Then we have to give it a different name so that we do not overwrite our old results, and I will add downsampling to it. So DS for downsampling. And then I click on OK. And then I hit run. We can again open the report here on the side and wait until the solver gets started with the first load case. You can see that the structure was resampled to a smaller structure. The voxel size of the edges divided by 4. That's the effect of the downsampling. So now the simulation runs on a way smaller structure and is therefore a lot faster, as you can see here. So the first load case is done. The second load case is done. Then the third. And so on. So that's a really, really easy way to speed up your simulations. It's maybe not what you should do if you need the highest accuracy, but especially if you want to screen several different models for example, the highest stiffness, then that is the way to go. Okay, now we can compare the results, because of course it was a lot faster, but the question is it also accurate enough? So first of all, we click on the previous result by holding the Shift button on your keyboard and clicking on a result, and then you can see those two reports next to each other. And then we can compare the results. So we scroll down to the orthotropic approximation. And there we see that in both cases it's more or less 82.78. So I think that's definitely good enough to use downsampling in this case. And we also can look at the log map that will tell us the runtime, and that's only a tenth of the original runtime. So you can 760 seconds compared to 70 seconds. So that's a quite huge reduce in runtime. And so now that we know that we can use downsampling, we can make a modification to our fiber structure and look what influence this modification might have. For example, we can change the angle of the fibers in the XY plane. And that is what we will do now. So minimize the result viewer. For those of you who do not have the FiberGeo results in the result viewer anymore because you closed it before, you can access them, for example, by right-click on the project folder, go on Open Project Folder, and then you can just drag and drop the FiberGeo result file into the user interface, and then there it is. And you can click on, for example, Load Input Map, and then all the input is back in the user interface. So we minimize it again, and we go back to FiberGeo. And in FiberGeo, we click on Edit. All those things, we leave them as they are, because the only thing we want to change is the orientation. There we go to Edit, and add an angle in the XY plane. And we had 0 degrees, but now let's say something went wrong with your process. For example, you did tape laying on the robot and the robot was not perfectly teached. So now you end up with a misaligned tape, and the misalignment is 5 degrees. And you want to know if your part is still stiff enough to perform its task. So we add 5 degrees. Then we change the file name. Remember, we called that 280 because of the domain size and 0 because of the 0 degree. So we change the 0 to 5. and we click OK. And then we hit generate. And of course, again, FiberGeo removes the overlap by moving the fibers around so that they don't overlap anymore. Okay, so now FiberGeo is finished, and we can close the result viewer and have a look at the structure. And again, we go to the 2D view and we slice through the structure. And now you can see that the fibers shift. Of course, that is due to the angle in the XY plane we defined. So we look again at the 3D view. And now you can see that we cannot assume anymore that a fiber which goes out on one side, for example, as this fiber, goes in again on the other side, because they have a slight angle, and that doesn't work anymore. And when you remember my explanation on periodicity, that now tells us that we have to use symmetric boundary conditions in the simulation, and we will do that. So we go to predict again, ElastoDict. So click on edit and choose carbon fibers as the fiber material. Always check if your materials are still white before you start a simulation. Then under load case, we have to switch to symmetric boundary conditions as I explained before. We do not change anything else except for the file name, in which we replace again the 0 by a 5. Then we click OK, and then we hit run. ElastoDict starts the simulation again. You can see again that we use downsampling. Okay, now the simulation starts. You can see that it needs a little bit more iterations, but it's still pretty quick. Okay, so we're already in a third load case. Okay. Now the simulation is finished. And then we look again at the stiffness. And by clicking on the other result file while holding Shift button, we can look at them next to each other. And here we can see that we have a decrease in stiffness of around 10 gigapascal, which is caused by the misalignment of our fibers of 5 degrees to the main direction. So those kind of things you can quite easily look at using elastotic rocks and maybe downsampling, and then you get an idea of how your material stiffness will behave. So after predicting the stiffness tensor of your material, we will now move on to large deformations and also plastic material behavior and failure. So you can close the result viewer, and we also clean up everything by going on discard structure and fields. So we have a plain canvas again, let's say. And what we can also do, I mean, now it's not a problem because it's just a file we made here, but if you have to show Geodict to some clients or maybe colleagues or someone who is not supposed to see the history of files down here, you can now click on clear recent files and folders, and then they are all gone. I think that's quite a nice feature. Now I will give you some background information on how plastic deformations in Geodict work. In Geodict, there are two different approaches for the simulation of deformation available. The first one is what we call without geometric nonlinearity, and it follows the theory of small deformations. And in the theory of small deformations, the deformations must be a lot smaller than the size of your structure, and because the deformations are that small, rotations are omitted. Of course, if you have a large deformation, you need the rotations. For example, if your fibers are supposed to align into a load direction, and then the theory of large deformation applies, and that is in Geodict behind with geometric nonlinearity. So with geometric nonlinearity, you can simulate large deformations. But there's also an option to use the theory of small deformations to simulate a large deformation in Geodict. And that is when you use the option undeformed geometry, which is indicated here. And I will explain to you in detail what undeformed geometry means on the next slide. The advantage of undeformed geometry is that you can combine it with both linear material laws and nonlinear material laws. So you have the option to combine a nonlinear geometric deformation with a nonlinear material law from the Geodict material database. Nonlinear material laws for the theory of large deformation means with geometric nonlinearity are not available in Geodict. Still, they can be used if you have an UMAT that supports large deformation. Okay, so what does undeformed geometry mean? The standard case is that you calculate on the original geometry. That means you have your geometry, for example, your fiber structure, and in the first iteration of your simulation, it is deformed, for example, by 1%. Then in the next step, Geodict goes back to the original geometry and deforms it by 2%, and so on. But because it always goes back to the original geometry, you cannot simulate, for example, the buckling of cell walls in the foam, and there can also not be a contact detection. For example, if you do a compression of a fiber structure, so maybe a non-woven, and the fibers touch during this compression, so that cannot be simulated. If you calculate on the deformed geometry, on the other hand, you have the original geometry, then it is again deformed by, for example, 1%. And the next iteration does not go back to the original geometry, but it only goes back to deformed geometry 1. And it takes that and deforms it by another 1%. And thereby you can get a gradually non-linear deformation during your simulation, and you have contact detection, and you can have also things like the buckling of cell walls. You can see also the comparison in these videos. On the left side is on original geometry, on the right side is on deformed geometry, and you can see that here the foam is just crushed without any bending or buckling or things like that, and here you can see that the cell walls deform. As I already said, there's not only non-linearity caused by the geometrical deformation, but also non-linearity caused by material laws such as plasticity. And in Geodict, there are three different kinds of plasticity available. You have the perfect plasticity, the bilinear hardening, and the exponential hardening. And those differ in their stress strain curves. So first we look at the perfect plasticity. And in perfect plasticity, you have a linear increase of the stress strain curve following the Young's modulus, and then it remains constant. because you have the perfect plastic deformation. The material is just flowing without any increase in stress. Then we have the bilinear hardening. Hardening means that although you reach the real stress here, the stresses still increase. And in the bilinear hardening, you have first the stress strain curve at the beginning in the linear section, which follows the Young's modulus, and then you have another straight line which follows the hardening modulus h, and that is the slope of this curve. And then third, we have the exponential hardening. In exponential hardening, the evolution of the stress strain curve after reaching yield stress is an exponential curve. You can see that here, and it is described by a more complex exponential plasticity law. And those three plasticity laws are available in the geodetic material database. For some materials they are already implemented, and if they are not, you can add them for your material. And now we use the plasticity laws for simulation.
So first of all, we have to make a structure again, and we do that with FiberGeo. And to that we click on Edit. And here, there are, at least in my case, still the settings from our previous structure generation. So if that is not the case in your user interface, please copy them, as you can see them here. And we will make one change, and that is that we change the number of voxels in x direction to 1 voxel. When you see the structure later on, I'm going to explain to you why we do that. We do not change the fiber options except for the orientation. There we go back to 0 degrees. And we change the name of a structure. I will call it 281 to indicate there is one direction with 1 voxel, and go back to 0 degrees. Then I click on OK, and then I hit generate. So that's a really quick structure generation because the structure is so small in x direction. And you can see the structure now. So we have like one slice of our structure with endless fibers. And if you remember, I explained to you that if we use periodic boundary conditions, it is as if the structure was repeated on all sides. So in this case, it is as if the structure was repeated in x direction endlessly. And by that, we again have endless fibers in our simulation without needing to model them. And that saves a lot of runtime. Of course, that is only possible if you have a periodic structure. But because we did eliminate the misalignment of 5 degrees and we only have 1 voxel, we can assume that every voxel that is on that boundary is also connected to another voxel on the other side. So we have a periodic structure, and we can assume periodic boundary conditions during simulation.
And what we want to do now is to run a simulation
with plastic deformation of the polymer. And to do that, we go again back to Elastodict. And we choose FIBAS LD for large deformations, because there you can consider the plastic material loss. And we click on Edit. And here now we have to choose our materials again. So for the polymer, we stay with the polyamide 6. We can also have a look at it in the material database. So click on Edit Material Database. So the material database opens up. And if you then go to mechanical properties, you can have a look at the laws for this material. And you see that there's elastoplastic at 23 degrees, at 80 degrees. So look at the Young's modulus. It's going to change with increasing temperature at 120 degrees and also 150 degrees. We stay with the 23 degrees. So here you can see that we have the Young's modulus, Poisson ratio, and we also have a plasticity model, in this case exponential hardening. And we have an initial yield stress at which the plastic deformation sets in. And we have isotropic hardening and the 2 hardening parameters which describe the hardening curve. And the hardening curve comes from a measurement. You can see that here. There's the measurement. And the material law was fitted to this measurement with the fit law parameters. We will do that later on. Not in this case, because in this case we will just use the material law from Geodict. So click on cancel. And we go with the polyamide 6. And here make sure that you have chosen elastoplastic at 23 degrees. And then you also need to activate the plasticity model. Activate exponential. Then we have to choose a fiber type. And there we again choose the carbon fibers. There we have the transverse isotropic linear elastic law, but that's okay for carbon fibers. They deform more or less linear elastically, so we can go with that. Then we go to the macroscopic load case. Here we can now define our experiment. What we want to do is a uniaxial tensile experiment. So that's already correct. And we are going to do it path controlled. That is the most stable way to do it, first. And second, that's also what a tensile testing machine does. It increases the strain on the specimen. Then we have to define the load direction, and we want to do it first in fiber direction. So we choose X. And then we define the shape of the load curve. You can have a linear increase of the strain or also a sine or a sawtooth, but we stay with linear. We want a deformation of 5% in 10 steps. And then don't forget to hit apply, because then this load table is updated with the iterations that come from this predefined shape. And you can also look at the graph. You can see here that the strain is going to increase up to 5%. For the boundary conditions, we choose periodic, as I explained before. Then we go to the solver tab. Again, we increase the tolerance. As solver, we have to change to the Neumann series, because the Neumann series can solve nonlinear problems. Parabolization, leave as it is. And again, activate downsampling just to make sure that your solver one finishes within a reasonable time in this workshop. And then click on OK. Then we click on Run. And you can see now that this is really quick because the structure is really small. And in addition, we use the downsampling. So we get a really, really fast simulation. Let's have a look at the results. In the report tab, we get tables with the average strain and the average stress. So that's what we wrote as result files. And then on plots, you can see the stress strain curve. And here you can see that although we added the plastic material law, the stress strain curve is almost linear. And that is caused by the carbon fibers. The carbon fibers are so stiff, and there is no failure considered in the simulation. So the stress just increases and increases. We can also look at the stress strain visualization. For example, at time step 3, and then you can load the solution file. Click on load. You can look at all the different fields you want to look at, and you click OK. And load them all. Then minimize the result viewer, and here you see our result file. We deactivate the structure again by click deactivating this checkbox. And here you can see now that we have quite high strains where there isn't much polymer between the fibers, so there are the stress peaks, and the fibers are not loaded that much. That's not a surprising result. We can also change the volume field we look at. So now we have von Mises strain. We could, for example, look at the von Mises stress. And there, due to the high contrast and loading of the fibers and the polymer, you see that the fibers take up almost all the stresses and the polymer isn't loaded much. We could also look at things like the plastic deformation. It's a little bit a cryptic name, but E+1 means plastic deformation in X direction. And there you can then see, because there is no plastic deformation in the fibers, because first it's carbon fibers, there is no plastic deformation, and second we have a linear elastic material law. You can see that the plastic deformation in the polymer is highest, also where the strains were highest. So here you can choose the results you want to look at. You can look at them. You can also, for example, clip so that you only see the highest values, and so on. We are now going to repeat this simulation for the Y direction, because there we should see more plasticity. And to do that, we go back on Edit. Okay, so now we go to the macroscopic load case, and we switch the direction to Y direction. Then we change the result name, we add a Y to the result name. And then we have to do one additional thing. I explained to you that our structure was periodic regarding the endless fiber. So it's periodic in the fiber direction, X direction. Because we did not generate the periodic fiber structure, it is not periodic in Y direction. But we do not want to use symmetric boundaries, because first they might have a longer runtime, and second we also want this periodicity effect in fiber direction. But what we can do is choose mixed boundary conditions. Mixed means that we have the symmetric boundary conditions in load direction, which we need, and we have periodic boundary conditions in the other directions. So we go to mixed. Then we click on OK, and then we click Run. And while the simulation is running, we are going to make our next 15 minutes break.